Hello, and welcome to this video on shielding gases in arc welding. You will find this video in the playlist for arc welding on this YouTube channel, The Weld Nugget. To begin with, let me start by sharing the screen so you can follow along on the PowerPoint that I'm going to share during this presentation. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. There are other videos in the arc welding playlist which might be of interest to you, especially the first one, the arc welding fundamentals, where we discuss the basics of arc welding processes such as GMAW and GTAW, which are the newer names for MIG and TIG welding. The other two videos include fillet weld measurements and shear failure in fillet welds. If you're new to the topic of arc welding, I would strongly recommend that you review the arc welding fundamentals video along with this one to get a better understanding of the subject. The number one job of shielding gas, as the name implies, is to provide shielding. So here I'm showing you a schematic. A weld is being made. This is a welding gun. The blue rod over here is the welding electrode, and it is supplied by electrical energy as well as shielding gas, which comes out of the gun. In this case, the shielding gas is shown as argon. AR stands for argon. Argon is an inert gas, which is commonly used as a shielding gas for welding. The main job of argon in this case, the number one job, is to push out all the other gaseous contaminants which can get into the weld, such as oxygen, O2, I've shown in orange over here, nitrogen, N2, as shown over here, and water vapor, H2O, as shown in red over here. All of these can get consumed into the weld and create detrimental zones or brittle zones and inclusions in the weld. Not all arc welding processes use shielding gases. The process such as SMAW, which is commonly known as stick welding, or SAW, which is submerged arc welding, do not directly use a shielding gas, though they provide shielding in a different way. In this particular video, we are only going to talk about arc welds which actually use a shielding gas. So the first job of the shielding gas is to push away all the potential contaminants in the environment, such as oxygen, nitrogen, and water vapor. The second job of the shielding gas is to provide a channel to create the arc so that the electrical energy can be conducted through that arc. So I'm showing you two schematics. The schematic on the left, again, shows a welding gun with a welding electrode and connected to the electrical circuit, and the argon gas is flowing. However, in this case, the voltage applied is not sufficient to produce a stable arc, and then hence the arc cannot form, and hence we cannot do any welding. On the schematic on the right, I'm showing you the similar circuit where we have a voltage which is greater than a required critical voltage for that particular length of the arc and that shielding gas. Once you're above that certain voltage, the shielding gas will ionize and create ions and free electrons, both of which are required for the current to flow from the electrode to the part. Ionization essentially means removing an electron from the atom. And so now the atom has a positive charge, and the free electron is floating around, has a negative charge. Ionized gas is required for the arc to conduct electricity. So the main reason for the arc to form is that is the only way electricity can be conducted from the electrode to the part. Keep in mind that when argon or helium is another of those inert shielding gases which is commonly used. Even when argon or helium are ionized, they do not actually react with the molten metal, or they do not dissolve in the molten metal. So even though they are physically there, they do not participate in any way with the fusion process. Their only job is to create the arc, which will generate the heat to melt the metal. Now let's see how this melting process works. Here again, I'm showing you a schematic on the left This is blue is the electrode. There's an electrical circuit over here. The voltage is applied, a current is flowing, and I'm showing two different resistances over here. Over here is the arc resistance of the arc itself. And over here is the resistance of the wire, which includes all the resistances, including the electrode and wire and connections and everything. So we can say that this circuit has two resistances, the arc resistance and the wire resistance. The arc resistance is a function of the ionizing voltage of the shielding gas being used, as well as the length of this arc. So this arc resistance can be changed by changing the shielding gas or by changing the distance between the electrode and the part. Usually, the arc resistance is going to be much, much greater than the wire resistance, or should be, because we want all the heat to be dissipated or generated in the arc, not in the electrical circuit. Now, here's an interesting aspect of two different shielding gases. When we do gas tungsten arc welding, or GTAW, and let's say we are passing about, say, 100 amps of current, you will find that the voltage for argon, if you're using argon as a shielding gas, the voltage required to initiate the arc is 14 volts, whereas the voltage required for initiating the arc with helium is 22 volts, about 50% more. And why is that? That is because helium is much more difficult to ionize, so it needs much larger voltage. And essentially, there is a much higher resistance in the arc when we are using helium. So by order of about 50%. So if you make the same weld with gas tungsten arc welding, and we do it with argon or helium, you'll find that the arc with the helium is producing almost 50% more heat than the arc with argon. Now, keep in mind that argon and helium are not the only choices. There are situations where we also use reactive gases, and that takes us to job number 3 of the shielding gas. So the third job of the shielding gas is to produce a desired mode of welding, especially in steels. Now, this following discussion on this slide is valid only for steels. So in steels, you're going to find that with GMAW, gas metal arc welding or MIG welding, you will have the opportunity to have 3 different welding modes. This is how the energy or the melt is transferred to the weld. First is called the globular transfer, which is using 100% CO2. So this doesn't even use any inert gas. This is 100% CO2, carbon dioxide. The plus side is it makes deep welds, but on the negative side, it creates a lot of spatter. So you make a very big weld, but a lot of spatter, which often is not expected in manufacturing operations. The other one is short circuit transfer, where we use a mixture of 75% argon and 25% CO2 typically. Some other ratios are also possible, but this is a common one which is used. Now, short circuit is great for welding thin parts and for out of position welding. So you can weld thin parts and parts with the out of position. That means vertical, overhead. Of course, it's not easy to implement. And oftentimes you're going to find that if you're in the manufacturing environment, you are most likely going to be using spray transfer. The spray transfer is the one on the right. It makes a narrower and deeper penetration right down the middle. And it works really well because it produces minimal spatter, and it is a very commonly used mode in automotive structural welding and similar manufacturing applications. So this is unique about steels. So you have 3 different modes in steels, and each one has a different application, though spray transfer is most likely going to be the one you are going to be using. So now let's look at a table where we put together all these in applications and see what would be the most typical common choice for a certain application. In this table, we have gas in the vertical axis, a vertical column, first one, the process in the middle column, and materials on the right column. For GTAW or TIG welding, almost always you use either argon or helium or argon-helium mix, no matter what metal you're welding, whether it's aluminum, titanium, nickel, copper, magnesium, or steels. So as long as you're doing GTA or TIG welding, you are almost always going to be using a inert gas or inert gas mixture. You can also use an inert gas mixture for MIG welding for all metals except steels. So if you're welding any other metal other than steel by MIG welding, such as aluminum, titanium, nickel, copper, magnesium, and so on, anything except steel with MIG welding, you will be using a inert gas or inert gas mixture, either argon, helium, or an argon helium mix. The only time you're going to use an active gas or reactive gas is when you're welding steels with MIG welding. So in this case, what I'm showing you on the orange, the last 4 lines, you can actually use 100% CO2 as a shielding gas. So that's when the globular transfer, as we have mentioned in the previous slide, we can use a 75-25 mixture of argon CO2 for short circuiting transfer and argon 10% CO2 mix for spray transfer. As I mentioned in the earlier slide, spray transfer is one of the most common and is most likely that you will be using in your application. We can also use argon plus 2% oxygen for stainless steel for spray transfer. So steels and stainless steels, the mixture used for spray transfer is a little bit different. The reason why we only use inert gases for TIG welding for all metals is because the TIG welding uses a non-consumable tungsten electrode. And we do not want the tungsten electrode to be affected by these active gases such as CO2 or oxygen. And that's why tungsten or GTA, TIG welding, is always done with an inert gas mixture. You can use GMA or MIG for with inert gas for all metals except steels. The steels are unique, and you have to use a particular ratio or mixture based on the type of metal transfer that you're expecting. In this table, I have only shown gas mixtures of 2 gases, but there are tri and quad mixes available now on the market. So tri mixes has 3 gases and quad has 4. So quad would be a mixture of argon, helium, a little bit of CO2, and a little bit of oxygen. But again, those are based on the application. So keep in mind, what I've shown you in the table over here are the most generic and most commonly used ratios of gases. Keep in mind that there's always exceptions to the rule, and you want to make sure that whatever your documentation says for manufacturing, so make sure whatever documentation you have, either a shop document or a WPS, and make sure you are following whatever that gas is being recommended in that document, which might be a little bit different than what I have shared over here. Now, how does active gas components actually work? The way they work is the active gas, like CO2 and oxygen, they actually decompose. So the energy of the arc actually decomposes the CO2 and oxygen, and CO2 breaks into carbon monoxide and oxygen. So you get a free oxygen atom over here, and oxygen also breaks into 2 oxygen atoms. So these free oxygens, they help to increase the fluidity of the puddle and helps wetting of the toes of the weld. So one of the main reasons why we have to use active gases for MIG welding for steels is this oxygen helps to increase the fluidity of the surface of the molten metal and helps to stabilize the center of the weld and helps to wet the toes at the edges of the weld. However, keep in mind that oxygen that may get absorbed in the weld puddle and sometimes may require antioxidants to be added in the filler wire to reduce inclusions and porosity. Some oxygen might also combine with carbon in the steel and be released as CO2. So some of the carbon could be lost from the weld puddle because of this presence of this free oxygen in the active gas. So selection of the gas composition requires careful testing and analysis. So there are many, many choices depending on the steels, depending on the filler wire, depending on the process. that you have to select the right gas for the right application. I had mentioned that primarily the active gases are essentially oxygen and carbon dioxide, but there are situations where you may have to use nitrogen and hydrogen. So unique application where if you're welding austenitic stainless steels are not affected by hydrogen. So you're not at the risk of hydrogen embrittlement. So you can use either nitrogen or nitrogen with 5% hydrogen as a backing gas. Now, the backing gas helps to keep the discoloration away from the weld and the heat affected zone. You can also use the argon plus 5% hydrogen for the actual welding gas. Again, for austenitic stainless steels, again, the presence of hydrogen helps to reduce oxides adjacent to the weld and produce a very clean appearance of the weld. In summary, inert gases such as argon and helium are commonly used for shielding gases for arc welding, such as GMAW and for GTAW. GMAW is the new name for MIG welding, and GTAW, or gas tungsten arc welding, is a new name for TIG welding. For steels and stainless steels, GMAW requires a reactive gas or a mixture, which includes some fraction of the reactive gas to increase the fluidity of the weld puddle surface so that you can have a nice profile and have nice wetting at the toes. Again, gas mix used for steels, there are multiple choices in there. You can have 100% CO2 for globular transfer, a different ratio of argon and CO2 for short circuit and for spray transfer. So the type of gas you select will depend on the type of transfer mode that you are interested in producing. Keep in mind that the active gas components in the gas, such as CO2 and oxygen, do decompose during welding. And though in one case, in some sense, they help with the welding by producing the fluidity of the weld puddle, they can also hurt by affecting the chemistry of the weld. So you have to make sure that all of those tests have been done before you recommend or choose a certain gas. There are exceptions to the rule, and nitrogen and hydrogen are as option for the backing gas or the welding gas when it comes to welding austenitic stainless steels, where hydrogen embrittlement is not an issue, and that can be an option, though it is very rare, but that can be an option. So thank you for your time. As we see on this YouTube videos, we have many other videos in the arc welding playlist and other playlists on this YouTube channel. All are related to welding and joining, and all are catering to engineering personnel who may not have a lot of experience in welding or might be new to the subject of welding. So please review all those videos, and please click the subscribe button at the bottom of the screen on the left over here. And wishing you the very best in your experiments with welding, and have a good day.